Hello guys, welcome back to my channel, and in this video I'm going to extend the Leibniz rule or the Feynman integration technique to some multivariable parameterized forms of integrals. So let's get to it, and you'll see in a while what I'm talking about. So like at the start of every video we have a problem, let's call it I, which is defined as the integral from 0 to pi over 2 of the natural log of 49 sine squared theta plus 81 cosine squared theta d theta. Now one thing you may notice here, that if we had say 49 sine squared theta plus, instead of 81 we had 49 again cosine squared theta, this would just be 49 because sine squared theta plus cosine squared theta make 1. But we don't have that, we have 81, which is quite different from 49. So using trig identities is not going to work, it seems, and also U substitution is not going to work because our initial integrand is quite complicated. We have a natural log of the sum of trigonometric functions which are themselves squared. So U substitution is going to make this problem integral even more ugly. And basically I think all other elementary integration techniques are going to fail here. So we are actually going to be using the Leibniz rule of differentiating under the integral sign, or you may know this as the Feynman technique of integration. So let's discuss the first step of using the Leibniz rule, which is finding a suitable parameterization on the next page. See you there. So now notice that there is no denominator in this original integral. So unlike our integral of sine of x over x from 0 to infinity, where we had an objective of getting rid of this denominator, so we introduced this parameterization, keeping into mind also the convergence of the parameterized integral over the interval of 0 to infinity. But our original motivation for introducing this parameter was to get rid of this x on differentiation with respect to t. Since there is no denominator here, there is no such motivation, or there is no such guideline that we have here. So this is out of the question. This thinking is out of the question. But one thing that you can notice, that we have a 49 which is a constant, we have a 81 which is a constant, and sine squared theta and cosine squared theta are variables. And since when we are talking of introducing fresh parameters, it's unwise to tamper with existing variables. So one alert, one warning that I would like to give you before we introduce any parameterization, this is more like a general warning, is don't tamper with the original variables when introducing parameterized forms. So in general, I mean, this could have some exceptions for some integrals, but I'm not going to discuss them in this video. So generally don't tamper with the original variables of with respect to which we were integrating. So in our case we were integrating with respect to theta, so don't tamper with variables that only have theta in them, generally speaking. So like, don't try to convert this cosine squared theta into something. You may try to put a parameter inside the argument of this cosine along, multiplied with the theta, but generally don't change the face value of any of this thing while parameterizing. So now one parameterization that I'm choosing, say I'll call that I of, now this parameter is a function of two different variables, or you can say this integral has two different parameters in it. So which is the integral from 0 to pi over 2 times natural log of, instead of 49, let's say t times sine squared theta, plus instead of 81, s times cosine squared theta d theta. So notice that, as I said, we should not tamper with these variables, original variables, but we never spoke about tampering with the constants, right? So that means you can actually tamper or play around with the constants. So instead of the constants, I've introduced these parameters over here, such that if you want to get back your I, you just plug in 49 in place of t and 81 in place of s, and you just get your original integral back. Fair enough. So now after we've selected our parameterization, let's go ahead and partially differentiate this. But the trouble is, it's quite confusing with respect to what should we differentiate I of t comma s, because there are two parameters. We can differentiate either with respect to t or with respect to s. So it's really up to you now which parameter to take for differentiation. But for this video, for our purposes, let's differentiate with respect to t, the first parameter. So when I differentiate with respect to t, I'll have to take a partial derivative with respect to t, because I is a function of two different parameters or two different variables. So we need to specify using this partial differentiation sign that indeed I of t comma s is a multivariable function. So same thing with this side, we have integral from 0 to pi over 2 of the partial derivative with respect to t of natural log of t times sine squared theta plus s times cosine squared theta d theta. And there is no simpler notation that we can write this, so let's just keep it as it is. And over here we have integral from 0 to pi over 2. Now time to apply the chain rule. So the derivative of a tangent of some quantity is reciprocal of that same quantity that was inside the argument, which is basically this thing, times, using the chain rule, we have to differentiate with respect to t the original argument, which is t times sine squared theta plus s times cosine squared theta d theta. Now on differentiation, we have integral from 0 to pi over 2 of differentiating s times cosine squared theta. We have no t expression, so this just goes to 0 by the properties of derivatives. Sine squared theta is a constant with respect to t, so that will come out, and the derivative of t with respect to t is 1. So we just have a sine squared theta divided by this original denominator, t times sine squared theta plus s times cosine squared theta d theta. Now I would like to divide the numerator and denominator by sine squared, so that we have sine squared divided by sine squared is 1, so we just have 1 divided by, again, t times 1, which is t, plus cosine squared theta divided by sine squared theta is cotangent squared theta, and we have a d theta as always. And I would like to slightly change this expression, this integral, into a more convenient form to work with. So I would like to introduce a substitution. So let u equal to cotangent of theta, such that du is negative cosecant squared theta d theta. So d theta is negative du over cosecant squared theta. How can we write that in terms of u? So notice that 1 plus cotangent squared theta is cosecant squared theta. So 1 plus u squared is 1 plus cotangent squared theta. That is exactly cosecant squared theta. So fine, we have expressed everything in terms of u. Now it's time to substitute. Okay, so when theta is 0, the cotangent of 0 is infinity, right? Because 1 over tan. And when we plug in pi over 2 in place of theta, we just have cotangent of pi over 2, which is 0. And we have negative, instead of d theta, we have du divided by this 1 over u squared factor, 1 plus u squared, times over here we have t plus s times cotangent squared is u squared, so s times u squared. Now using one of the properties of definite integration, I would like to suck up the negative and flip the upper and lower bounds. So now we have integral from 0 to infinity of du over 1 plus u squared times t plus s u squared, and we have I of t comma s but differentiated with respect to t. All this is just equal to this. Fine, but we want to convert this integral that we obtained into a much more convenient form, because we also have to reintegrate with respect to t, right, according to the steps of Leibniz rule, applying Leibniz rule. So looking at the situation in the denominator, I feel it is a good time to use partial fraction decomposition. So let's do that on a fresh page now. So for partial fraction decomposition, let's just forget the integral for now. We can integrate everything after performing partial fraction decomposition. So just look at the integrand now. So we have integrand as 1 over 1 plus u squared times t plus s u squared. Now that can be broken down into 1 plus u squared, and we need a linear term, right? Basically we need a term which is of a degree 1 less than the denominator. So our denominator has a degree 2, it's a quadratic, so we need a linear on top of degree 1. 2 minus 1 is 1. So let's call our linear term au plus b, plus we have now the second factor t plus su squared, and we also need a linear again, so cu plus d. Now we can cross multiply on the right hand side and cancel out the denominators on both sides. So we have 1 is equal to au plus b times t plus s u squared plus cu plus d times 1 plus u squared. So now just grouping terms with the same u values. So we have u cubed as multiplied with as plus c plus u squared, which has a coefficient of bs plus d, plus u which has a coefficient of at plus c, and a constant term which is basically bt plus d. So now time to compare coefficients on both sides. So since there is no u cube term on the left hand side, as plus c is also is 0, and there is no u term on the left hand side, so this term at plus c should also be equal to 0. So that means that a times s minus t is equal to 0 if we subtract the second equation from the first. So since s and t are parameters, we can't necessarily assign values to them directly. We can't just say that s is equal to t. That would be like a special case of parameters, and let's not deal with special cases just as yet. So if s minus t is if s is not equal to t, s minus t is not equal to 0. That means a has to be equal to 0. Fine. Now plug it back into this first equation. So we have a times s, which will be 0 because a is 0, such that we obtain c is also equal to 0 now. Okay, nice. Now we have this term, this constant term bt plus d, that is equal to 1 because 1 is the only constant we have over here. While there is no u squared term, so the coefficient of the u squared or bs plus d has to be 0. Now subtracting the second equation from the first, d's will go out. We have b times t minus s with a 1 here. So now dividing both sides by t minus s, we have 1, b is equal to 1 over t minus s. Now using this first equation over here, we have d is equal to 1 minus b times t. We know b, just multiply a t, so we have t over t minus s. We just simplify this, t minus s minus t divided by t minus s. The t's will go out. We have a negative s over t minus s. That's basically your d. So we have found out our values for a, b, c and d. Now it's time to plug them back into our original expression of partial fraction decomposition. This expression. I'll just clean this up now and let's plug that in. So by our procedure we found out that a and c are 0. So this goes to 0. This goes to 0. So we are only left with a b divided by 1 over u squared term. So what's b? B is basically 1 over t minus s times this denominator. So 1 over 1 plus u squared plus we just have a d. And what's d? D is negative s over t minus s times this denominator. So 1 over t plus su squared. Well, fair enough. Now let's integrate both sides from 0 to infinity with respect to u, as we had in our original problem, original partial derivative expression. And don't forget the du's, guys. It's important notation. So now notice that the 1 over t minus s terms will come out because they are constants with respect to u. So 1 over t minus s times integral from 0 to infinity of du over 1 plus u squared. And the plus and a minus will make a negative. Even this is a constant. So s over t minus s outside times integral from 0 to infinity of du over t plus su squared. Now this is just inverse tangent, right? The antiderivative of this thing. So we have 1 over t minus s times the inverse tangent of u from u equals infinity to u equals 0 minus s over t minus s. I would like to take an s out of this denominator. So 1 over s times the integral from 0 to infinity of du over t over s plus u squared, to maintain equality. So now inverse tangent of infinity is just pi over 2 minus inverse tangent of 0, which is 0. So we just have pi over 2 times 1 over t minus s as the antiderivative of this thing, or the definite integral of this part. And these s's will cancel out. So we have negative 1 over t minus s times integral from 0 to infinity of du over u squared plus. Now I would like to express this as t over s, but the square of the root of that. and that's because we have a particular formula, the antiderivative of expressions like these, that involves the inverse tangent. So we have 1 over t minus s times the reciprocal of whatever was squared, so that will be s over t times the inverse tangent of u divided by whatever was inside over here, that will be square root of s over t, flipping it back up, evaluated from 0 to infinity. So now simplifying everything, we have pi over 2 times 1 over t minus s minus 1 over t minus s times square root of s over t, and when when u tends to infinity, we have infinity times some constant that will also be tending to infinity, because infinity is a really large number. So we'll in totality have the inverse tangent of infinity, which is pi over 2 minus the inverse tangent when u equals 0. And when u equals 0, we have 0 times the constant, which is 0. So inverse tangent of 0 is 0. So we have pi over 2 minus 0, which is just pi over 2. So now we can take a bunch of things common over here. We can take pi over 2 times 1 over t minus s as a common factor, while we have 1 minus square root of s over t. So now obtaining a common denominator, we have pi over 2 times 1 over t minus s times square root of t minus square root of s divided by square root of t. But there is, however, one more simplification that we can do. So we have pi over 2 times 1 over, I can write this as square root of t but the whole thing squared minus square root of s but the whole thing squared times square root of t minus square root of s divided by square root of t. Now I can use the difference of squares identity on this denominator. So we have 1 over square root of t plus square root of s times square root of t minus square root of s times square root of t, there was a minus square root of s divided by square root of t. Now notice that nicely this and this is cancelling out. So finally we have pi over 2 times 1 over square root of t plus square root of s times 1 over square root of t. So basically finally the partial derivative with respect to t of this parameterized function I of t comma s is just equal to pi over 2 times 1 over square root of t plus square root of s times 1 over square root of t. So now to obtain again an expression of I of t comma s, we need to integrate with respect to t, but this time, unlike all our other Leibniz Rule videos, we're going to integrate indefinitely, not definitely. That's because remember what I of t comma s originally was. It was the integral from 0 to pi over 2 of the natural log of t times sine squared theta plus s times cosine squared theta d theta, and calculating upper and lower bounds where this integral is going to be 0 and where it's going to have a certain value is going to be tricky, because there are two parameters, right? Although we'll be integrating with respect to t, it will be hard to how to handle both of the parameters at the same time, because we need t and s to have certain values for us to go back to our original problem I, which will be t equals 49 and s equals 81. So we need to handle two parameters at the same time. So instead of finding suitable upper and lower bounds to our integration, let's just integrate indefinitely and then we'll obtain a constant of integration by default, and we'll get rid of the constant of integration by doing some background computation later on. So as I said, let's integrate this with respect to t. So we have indefinite integral now of the partial derivative with respect to t of I of t comma s integrated with respect to t being equal to pi over 2 is a constant, pi over 2 times indefinite integral of dt over this expression square root of t plus square root of s times square root of t. So now by the fundamental theorem of calculus, it's almost like the partial derivative with respect to t and the indefinite integral with respect to t are sort of cancelling out. So we just get I of t comma s being equal to pi over 2 times integral with respect to t of square root of t times square root of t is just t plus square root of s times square root of t. Okay, now we can still convert this into a much more convenient form by performing certain substitution, because now look at the denominator. It would be great, it would be nice if we could get rid of this square root of t term. So let's perform a substitution accordingly. So because we want to get rid of the square root of t, let's say let t equal y squared such that dt is nothing but 2y dy, and since it's an indefinite integral, we don't worry about the upper and lower bounds, except that we'll have to back substitute after we get an antiderivative. So integral of, instead of dt we have 2y dy divided by, instead of t we have y squared plus square root of s times square root of t. If you can reconvert this, is y is equal to square root of t. Instead of square root of t we have a single y. Now notice that this 2 and this 2 is cancelling off. We can cancel off one y each, so this y goes with this y and this y. So we simply have pi times indefinite integral with respect to y of y plus square root of s. And now notice that this is simply a linear term. So we can go ahead and find the antiderivative of this, which is pi as it is times the natural log of absolute value of y plus square root of s plus the constant of integration c. But we have to back substitute for y. What was y? Square root of t. So we have pi times the natural log of absolute value of square root of t plus square root of s plus c. Actually we don't need the absolute value because square root is going to be positive according to our convenience. So this is basically an expression for I of t comma s along with the constant of integration, which we need to get rid of soon. But one great point worth noticing is I of t comma s is this weird function with the constant of integration, but that is exactly equal to I of t comma s, which we originally defined, right? Basically this parameterized, double parameterized integral. So let's set them equal to each other because they indeed are equal to each other. So now we have integral from 0 to pi over 2 of natural log of t times sine squared theta plus s times cosine squared theta d theta being equal to pi times the natural log of square root of t plus square root of s plus c. But let's use a certain trick now. Let t equal s on both sides, obviously. Let's make the two parameters equal. So this is a special case when both of the two parameters are equal to each other. And let's see if we can find a nice value for c if this integral simplifies, and then we can subtract both sides with this expression over here. So when we do that, we have integral from 0 to pi over 2 of natural log of t times sine squared theta plus t times cosine squared theta, because both of them are equal, the parameters, d theta, and we have pi times natural log of square root of t plus square root of t plus c as it is. C is the constant, is unchanged. So now notice we have integral from 0 to pi over 2 of natural log of cosine squared theta plus sine squared theta is going to be 1. So we just have natural log of t d theta we have over here is equal to pi times natural log of square root of t plus square root of t is 2 times square root of t plus c. Since natural log of t is a constant with respect to theta, we just have natural log of t, and when you find the antiderivative of this is just theta evaluated from pi over 2 to 0, and here we can split this up into pi times using properties of natural logs, natural log of 2 plus natural log of square root of t plus c, and now this becomes pi over 2 minus 0, which is nothing but pi over 2. So pi over 2 times the natural log of t is equal to pi times the natural log of 2 plus square root natural log of square root of t. Square root is raised to power half. We can bring the power down using properties of natural logs, or logs in general actually. So we have half of natural log of t, half with the pi is pi over 2 times the natural log of t plus c. Now notice that these two things are cancelling out nicely to give us that our constant of integration c is just equal to the negative of this thing, right? If we put that on the left hand side, negative pi times the natural log of 2. That's our constant of integration. So now we can plug this constant of integration back into this expression that we obtained by using the Leibniz rule, and that will be our complete expression of I of t comma s. There will be no ambiguities or unknown constants anymore. So basically our I of t comma s is going to be this initial term of pi times the natural log of square root of t plus square root of s plus the constant of integration, which we know to be negative pi times the natural log of 2. So now let's just use some log properties. We have pi times natural log of square root of t plus square root of s minus natural log of 2. So using log properties, we can write this as a quotient inside the argument as the natural log of square root of t plus square root of s divided by 2. And as I said, we don't actually need the absolute value because our square roots are going to be positive as per our definition. So this is our value for I of t comma s. But remember what our original problem was. Let's go back and see. So our original problem was basically, let's scroll up a bit, I of 49,81, right? As per our parameterizations and our choice of constants in our original problem. So 49,81. So when we plug that in, I of 49,81, that is going to be pi times natural log of square root of 49 is going to be 7 plus square root of 81 is going to be 9 divided by 2. So you have pi times natural log of 16 by 2, which on performing basic division is going to be pi times the natural log of 8. That's your I of 49,81 or your original problem. So that's a really nice result. We have a pi and a natural log. The pi's can, you can still expect pi's having sines and cosines in the original integral, but this natural log is pretty unexpected again. And finally, for the sake of completion, we have I equal integral from 0 to pi over 2 of the natural log of 49 sine squared theta plus 81 cosine squared theta d theta, that is just equal to pi times the natural log of 8, which you can express as 3 pi times the natural log of 2, because 8 is 2 cubed, you can bring the power down. And basically we used multivariable extension to our Leibniz rule or Feynman integration technique, and we obtained this answer because we dealt with 2 parameters instead of 1. You could have probably done this using just parameterizing one of these constants, but I don't know, I just found this solution way more elegant. And I mean, we have to grow up, right? We have to grow up from single variable calculus and move on to multivariable calculus. And I think this choice of 2 parameters instead of 1 was really a nice way of showing that. So that's it for this video. Guys, please like, share and subscribe to my channel. You can follow me on Instagram. I have this username of gamma_digamma. And stay tuned for more content. Please recommend me to your friends. I really need to grow. I need more subscribers. I need more viewers and everything else. So in the meantime, stay home, stay safe. Peace out. Have a great day.